Hi, so I wanted to talk a little bit today about the famous n choose k formula. So n choose k should be equal to n factorial over n minus k factorial times k factorial. And what I found when I first was introduced to this formula, I would always find that this part was fine. I was okay with this part of the formula. So this n factorial over n minus k factorial, we know that that is the number of ways of choosing k objects from n where order matters. Yep. Okay, the part that was always not necessarily confusing. It was always, in some respect intuitive, but hard to see exactly where it came from, was this k factorial factor. Now, most of the time, I think this was sort of explained away with an aside, something like, and then you just got to divide out by the permutations, right? And that's all well and good. Like I said, it's not necessarily that it's super counterintuitive or weird or anything like that. It makes sense, but where exactly is this coming from? How exactly do we get this k factorial? For example, if I'm dividing out by it, well, when was I multiplying by it, right? And so actually, to make this crystal clear, it's maybe a lot easier than younger me might have thought. But literally, I think it really comes together when you write the formula this way. Ah, so much nicer, yes. And if you can already see the logic behind this at this point, I mean, you can just turn this video off and boop, we're done. Because at this point, I think this way of writing the formula, it makes a lot more sense. So once again, we already know what this side of the formula represents. We know that that is just the number of ways of selecting k objects from n where order does matter. Now, just to kind of, really hone this in here. This side of the formula, let's suppose that we don't actually know yet what n choose k is. We don't know the formula for it, I should say, yet, right? But conceptually, we know that this is the number of ways of choosing k objects from n where order doesn't matter this time around. And if you want like a slightly more rigorous definition, right? Because this all feels very sort of physical, like, Bob from, wherever is asking for this or something. But you could also think of this then as the number of k element subsets of an n element set. Right, but anyway, going back to what we were saying, this is where order doesn't matter, right? It's the same concept from n, we're selecting k objects, but this time we don't care about the order. Okay, and just to kind of illustrate, what's going on here, we could say, let's suppose we had this set 1, 2, 3, 4, 5, right? And let's say I'm picking 3 elements at a time, right? So let's say I had this set 1, 2, 3. For me, if I don't care about the order, that's the same as, say 2, 3, 1, and 3, 2, 1, and so on and so forth. There's lots of different ways of rearranging this. But to me, these are all going to count as just 1, right? These only supply 1 to the count. I really don't want to count this multiple times because although the order is different in each one of these, they're the same elements. It's a 1, a 2, and a 3. A 1, a 2, and a 3. And like I said, I don't really care about the order. And now we see that the number of ways of doing this is n choose k, right? That was how we, in some sense, defined it. N choose k is just the number of ways of doing this. So there might be another way of doing this. Say maybe I pick 4, 2, 5, right? That's just another way of doing it, right? I could write that as 5, 2, 4. But again, these are just equivalent to me. What's not equivalent are these up here, right? 4, 2, 5 is very different from this one. It's different from that one. It's different from, these are all very, very different, right? And I can keep doing this. But with that said, if I enumerate all the way down, I'll have n choose k of these ways of doing things. And you can think of this as sort of like, unique selections. From this collection of 3 elements from this set, there is at least one element in here that's not in there, right? Because these are not going to just be reorderings of the same thing, right? And that's true as I go down vertically. But horizontally in each one of these, it's just a rearrangement of the same elements. I'm just permuting them, right? And so, with that said, this is sort of the number of ways of uniquely selecting 3 elements, right? And there's n choose k of them. But what if I did care about order now? What if, for me, 1, 2, 3 was different from 2, 3, 1, was different from 3, 2, 1. I want to start actually counting these, like this would be 1, this would be another one, this would be another one, and so on and so forth. Well, if I did that for this entire choice, sort of, you could think of this in some sense, if you want, as if you take the set of tuples, 3 tuples here from this set, in other words, where order matters, you could think of this as almost like an equivalence class, right? The equivalence relation here being that they have the same elements. You could actually show that that's an equivalence relation, if, that's something that you want, if you wanted to make this a little more rigorous. But in any case, what if I care about the order here, these permuting, changing the order of these things? Well, we know that since there's 3 elements here, there's going to be 3 factorial. And to generalize, that would be k factorial. If instead of picking 3, I was picking 4, and instead of this being 5, it went up from 1, 2, all the way up to n, right? So from the n, I'm picking k. In this case, it was 5 and 3. Right, so there's k factorial here. And that will get me all the ways of selecting these numbers 1, 2, 3, and all of their permutations. In other words, it's really all the ways of selecting this particular collection where order does matter, right? And I could do that for down here as well, k factorial, and I could keep doing that over and over and over again for all of these. For each one of these unique selections, I'll sort of keep permuting them and counting those permutations, and I'll get k factorial every single time. And if I add them all up, k factorial plus and so on and so forth plus k factorial, let's see what I did. How many of these were there? There were n choose k. And I'm adding k factorial that many times, so that's n choose k times k factorial. But now look what I actually have over here. I have all the ways of picking 1, 2, 3, and its permutations. All the ways of picking 4, 2, 5, and its permutations. And I'm doing this for each unique selection of 3 elements from my set. In other words, when I'm doing this, adding up all the k factorials, what I'm really saying is all the number of ways of picking k elements from n where order does matter. But we already said we know what that is. Number of ways of choosing k from n where order does matter. That's this right here. And that's really all there is to this formula, because now you can just divide out by this k factorial, which was, I guess, that aside that maybe I was just too dumb to realize. But this is where the dividing out by the permutations comes from, right? So I hope that maybe that was elucidating something that maybe you didn't see before, like me. Hope this helps, and I'll keep making more of these, so take care.